minutes. Kevin will figure it out. Kevin, did you try the mute button? Because the mute at the top, it just looks like it's clicked. You did? Yeah, the technical challenges. Because I can't, since it says you're muted, I can't unmute you. It's grayed out for me. And I can make it a big screen. Anyway, welcome. So this is the second hangout. I know we had some challenges with some of you with the scheduling for last week and technical challenges that sometimes still continue, but this is our hangouts, our weekly gab session for digging deeper into what we've talked about and where we are with the source material. I know everybody's sort of at different places as far as background, so with Kevin and Abby, you might feel like you're a little bit thrown in feet first, and hopefully for Phyllis and Sue, you're a little bit more up to speed. But I'd like to make sure to bring you guys along, make sure everybody's paying attention, or not paying attention, but able to follow along. I hope you're paying attention. Yeah. So we can generally, I just like to open it up to question and answer session. See if you have any questions about specific content. As we discussed last week, that this class will be at a slightly slower pace just because the session has an extra week. So only 2 lectures a week, so it won't completely consume your time. Yesterday, even though it was the 4th in the States, Sue's Canadian. You guys don't hold that against her. I mean, I know you can't tell. She's secretly Canadian. She almost looks like an American, but she's probably one of those Canadian terrorists. Lecture came out yesterday on really working in the calculations, and I know to those of you who are new that the calculations are sort of an abstract thing, but it's really the language that we use for talking about the chemistry of glazes. And again, you can go back and review some of that previous content in some of the Lecture 1 videos, specifically video 7 on Stall and and I closed my other window, Google Chrome, and then I think it's video 8 on doing the calculations. So, does anybody have anything as we proceed? Any questions so far?
I have one simple one.
I will give you an hour-and-a-half long answer.
All right, you do that. You probably will. So this morning when I listened to you this morning, you talked about how the color and texture could be affected by, I'm assuming, lithium, sodium, and potassium.
Mm-hmm.
And then you also meant, now I can understand the color, but the texture.
Mm-hmm.
What are you referring to as texture? Is it like in drawing where they get fuzzy and?
Sort of. But what I actually mean is the actual qualities of gloss and matte, along with in matte glazes what type of crystals you're going to precipitate and that sort of thing. Start with glossiness. We sort of can just say, oh, well, glossy is glossy, and we sort of assume we know what that means. But there are actually serious levels of intensity when we talk about glossiness. And that's going to come up in 2 lectures, I think, maybe 3, where we'll talk about how using different fluxes creates just different levels of gloss. And this isn't even talking about different textures of matte. Literally just how shiny you can get them. And shininess is important, okay? A lot of people, when you're talking about a glossy glaze, if you're looking at it sort of unobjectively, maybe we don't see a lot of surface variations, but a lot of glossy glazes will have waves or dimples or divots, and they're things that will diffract the light so that the glaze doesn't look as glossy. And this is something that we're always fighting, because again, the really important thing I sort of want you guys to wrap your head around at this point is going back to this notion of we don't need the fluxes to get glass. right? That if we had a kiln that would go to 1700, the glass would form just fine. Okay, but we need fluxes to bring that temperature down, okay, into our working range. But what that means is that there's actually limitations to how powerful those fluxes are. Okay, and so different fluxes will have essentially different levels of power. So lithium, being a very small molecule, is very, very active. Now, some people would say that it melts at a lower temperature. As we go on, we're going to get into the subtlety of what temperature means, and is something really melting at a lower temperature. Spoiler alert, I hesitate to say that. But it's a very powerful flux. So you tend to get glazes that are very, very glossy when you're using lithium as your flux. Whereas because potassium is such a large molecule, the glazes tend to be not as glossy. Okay, because the actual, for lack of a better term, the kinetic melting behavior of potassium as a flux is less than the kinetic melting behavior of lithium, and of course sodium ends up in the middle. The other part is that the same thing is true in reverse for the alkaline earths. Okay, so magnesium, you try to make a 7-to-1 glossy glaze with magnesium, it's not going to be particularly well fluxed. It's going to have sort of a lumpy oatmeal texture, and even in the gloss region. Whereas if you have a barium, and I just happen to know, again, this doesn't do much, but like this is a barium gloss, and it's, if I can catch the reflection of you guys in the tile, like this is really, really glossy, and this is a barium fluxed gloss. Okay, and it's the fact that barium is so large actually allows it to not be heavily fluxed. Add on to that, zinc is actually sort of a strange little beast, and in the right proportions, zinc will actually be a very active melting material. And that, again, this comes up in 2 or 3 lectures. But when we consider the actual quality of the gloss that we're generating, it is dictated. Now, of course, if we're talking about lithium, we automatically hit the studio problem of that spodumene petalite suck as a lithium source. They're really low lithium content in their chemical analysis. They tend to foam in the glaze. They tend not to mix well in the glaze. And of course, we don't want to be using lithium carbonate because soluble carbonates. Although that will come up at the very end of the course when we start to talk about 04 sculpture glazes and all the crazy things people do in those. Because, yeah, when it comes to 04 sculpture glazes, like, the rules, they're just gone. They're just like crazy, go nuts. But we'll talk about some of the tricks that they're doing to make that happen, because I think it helps us wrap our head around some of the flexibility we can have, the intellectual creativity we can have with some of that chemistry. Did that answer your question at all?
Yeah, so you're referring more to gloss, the dimples, not like hare's fur and effects like that.
No, hare's fur. Actually, hare's fur we get into specifically down the road, and we would call that under a special effect. And a hare's fur will come under a condition called phase separation. And phase separation is getting inconsistent effects or non-homogeneous effects. So where in hare's fur, where it's regional. Or based on thickness, or based on layering is a big phase separation effect, where technically phase separation is when your glass, so I always talk about with a matte glaze that it's crystals growing in a gloss, right? And that's assuming that it's homogenized, that all the glass forms crystals evenly. Phase separation is the same notion, but actually what happens in your chemistry is that it forms 2 completely different materials. It's actually called a 2-liquid stage. And it's inconsistent, it's random, it's very popular in the artist community because it creates break, it creates visual texture, variations in color, variations in matte textures, special effect, defect, somewhere in there. It can be very controllable, but we'll get into that. That's like a big talk. What I was talking about, though, with the flux selection and texture, again, this will come up as we go. But that gets into the fact that specifically we talk about crystallization, right? When we are crystallizing out a matte glaze, we are precipitating crystals. And they tend to be some sort of species of uh, um, silica, alumina, and the alkaline earth. Okay, whatever is the alkaline earth in our glaze then dictates the type of crystal. And when I say type, I literally mean the shape of the physical crystal is dictated by which alkaline earth. And so each of our crystals, each of our alkaline earths has actually at least 2 different types of crystals that it forms based on composition. Again, we get into this in depth as we go a few lectures down the road. So that's really where it affects texture, but you can use the same trick to when you're inducing phase separation, and of course as color will become the big one. Oh, good. That's everybody's questions. Great. Awesome. Sue, did you have a question?
Not really too much. I'm pretty excited to learn more. I'll probably have lots of questions eventually. But more about my experiments.
Mm-hmm.
I have questions about that. You said something about solids loading, and I don't know much about that. And I don't know, are we going to cover like dispersants and specific gravity and that sort of thing?
We will cover dispersants somewhat. I don't talk about specific gravity a lot, only because it's a relative concept. Specific gravity, for those of you who know or don't know, is all water has. I like to use density, especially density and specific gravity are essentially the same thing, kind of. Water has density, and density is how much material you can fit into a specific volume. So water is measured in grams per cubic centimeter. So if you've got 1 cubic centimeter, like literally a tiny little cube made of that is 1 centimeter in every direction, what does that weigh? Okay, and for water it always weighs 1. As you add things into water, okay, the specific gravity goes up, and that's a way to measure, for lack of a better term, how thick your glaze is in the raw state. Different glazes all have different specific gravity based on what's inside that glaze. So something with, say, high clay content tends to have a very high specific gravity because the clay makes the glaze thick, and so it changes. And so to that end, it's sort of impossible to say specifically what specific gravity a glaze should have. Okay. It really depends on what is the glaze, what is the composition, and what is your application method. Okay. So for background for everybody, Sue is going to work on an experiment where this is a discussion she and I have been having, and another guy, Peter, have been having for a while now about what causes pinholes. Okay, and pinholes are the little bubbles, popped bubbles that you see in a glaze. And in Glazes 1, I talk about how my friend Dave Finklenberg did his master's thesis under the notion that pinholes are I should step back. It's been commonly believed that pinholes are caused by gas escaping from your glaze or from your clay body during the firing. This gas forms a bubble, and the bubble pops. The problem is that Dave's thesis basically states that defies the laws of physics. Like it literally, cannot happen under, the basic laws of physics. And so Sue, last winter, had done some experiments with a glaze trying to eliminate pinholes and had what I would call very promising results. Sort of indicating that it really is not based on gas evolution, where she made some physical changes to a glaze, not chemical changes, and was able to eliminate pinholes. Am I recreating what happened pretty well?
Yeah, yeah.
Okay. So what we want
What
to
were
do...
the physical changes?
Go ahead. Sue? You wanna...
So I just added Darvin as a dispersant to thin out the glaze. So I don't really understand why it worked, but I tried it and it worked pretty good.
Well, why it works? Okay, so going back to the theory of why pinholes exist. Okay, what Dave's theory is that pinholes actually form as trapped air in the glaze application. Okay, so when you dip your glaze, we'll just say it's a pot, and say you dip that in a bucket, that you trap a fair amount of air inside that thin layer of raw glaze. And what Dave's theory is that if you're trapping air, then that air pocket sort of gets trapped when the glass in the glaze melts, and then sometimes it ruptures on the surface and you see it as a pinhole. And Dave's theory really, really checks out. The first number one reason of why his theory is so great is because this notion that gas escaping from the firing creates pinholes, it's just nonsense, because Dave's thesis is very basic of can you have pinholes on the bottom of a plate? And the simple answer is yes, of course you can. They happen all the time. But if the bottom of a plate is upside down, essentially, and gases rise, which is a law of physics, then you literally should not be able to have gases that are rising through the bottom of your plate. Again, that's the defying the laws of physics. Along with the fact that the pressure of a gas bubble would create actually can't rise through a glaze because glass is much too thick. It's too viscous of a liquid. Anyway, it gets into the subtlety of it. So what did we do with Sue? We took this glaze that just was known to pinhole, right? And it was just a beast. Woo yellow, right? And so we added Darvin. I say we. This is the classic. I say we, and Sue did all the work. Sue added Darvin to this glaze, and what Darvin does is it's a dispersant, okay? And dispersants make the particles in your glaze pack tighter, okay? And again, that the subtlety, the exact subtlety of a dispersant. You can, so say you've got, say these are our clay particles. One side is positive, one side is negative. Okay. What a dispersant does is that it coats the positive side and turns it negative. Okay. So now you have a negative. So in the clay, the positive sticks to the negative and everything sticks together, and that's why clay works as clay. But if you reverse those charges and try to stick a positive to a positive, just like any magnet, they repel each other. What Darvin does is that it temporarily turns all sides positive. Okay. And so the clay particles no longer repel each other, and all of the particles in the glaze mix actually pack better because there aren't agglomerates of clay. So by adding dispersant to Sue's glaze, we essentially just made all those particles get closer together, and that meant that there was less empty space inside the glaze, less of an opportunity for those bubbles to form in the application. And if the bubbles don't form, you don't get pinholes, which is what we saw. As soon as you took the same glaze and made the physical particles of raw minerals packed together better, the pinholes went away. Because, again, it proves that it's not gas evolving from the glaze, because it's the same glaze. It's not gas evolving from the clay body, because it's the same clay body. And besides the fact that both of those literally violate the laws of physics, and I don't know about you guys, but I respect the laws of physics. Until Doc Brown shows up with the time machine, I'm gonna stick with them. They've seemed to have worked pretty well so far, and so it's a great theory. So what we've been talking about is Sue's gonna take this experiment a little bit farther for her research, and we're going to try. Two glazes probably go with the woo yellow again and something else.
Yeah.
And actually, I was thinking we probably should just go with like a 4-3-2-1, just like something super generic and basic.
Sure.
And so we'll take 2 glazes and 2 different clay bodies. And what we want to look at is how the bisque of her clay affects the glaze application. Okay, because as you bisque your clay, so our clay is actually full of a ton of empty space. In fact, your clay that you make a pot from and then dry is 30 to 40% empty space, just air. Now it looks like a solid thing, but it's just open pockets of air. So as you bisque, you actually shrink those pockets smaller and smaller and smaller, and that's the shrinkage that you get in a bisque, and you generally get about 3% shrinkage in a bisque. Okay, so the pockets of air get smaller and smaller. So what we're going to do is we're going to take several clays and we're going to bisque it to different temperatures, making those air pockets smaller and smaller and smaller. So one of the theories as to why we get these air bubbles in the glaze is because when you dip your pot, good pot here, when you dip your pot in the glaze, right, the pores in the clay body suck up the water really quickly, and then the glaze that was contained the water then sticks to the pot surface. Well, this theory is if we change the size of the pores, making them smaller, the application rate will be different. Okay, if you've got lots of big open pores, they suck up water really fast, like a dry sponge. But if you make the pores smaller by bisquing hotter, okay, they will soak up slower, like a damp sponge. Okay, it'll still soak up liquid, but not as fast, giving more of an opportunity for bubbles to form. So hopefully, this will force some pinholes.
Right. So.
Okay, go ahead.
So you would predict that bisquing at a hotter temperature would create more pinholes than a lower temperature?
No. The opposite.
Oh.
Because the lower ones are going to suck up the air really fast.
Okay.
And that's going to not allow the particles to arrange themselves in a compact manner, which is what the Darvan does.
Right.
So if it has more time, if it's a slower absorption of the water, the particles can, sort of, it's like a traffic jam, right? If everybody has to slam on the brakes, then boom, 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 boom. But if you have the time to put on your brakes, everybody can stop, and line themselves up before it happens. So I think that the lower temperature bisque will have more pinholes.
Oh, okay.
At least that's my theory. I'm always willing to be wrong.
Yeah. So I don't understand with the Darvan, if it's making everything positive, then why are they not repelling each other?
They are repelling each other.
With the Darvan?
Mm-hmm. But only the clay particles.
Oh.
Okay, the Darvan... Oh, go ahead.
No, I'm just processing. I can't quite wrap my head around it.
Processing. You guys are so cute. Such a cute little country.
Processing.
Processing. No, I don't mean to condescend to an entire nation. You all come after me smelling of poutine and Molson. It does. Okay, but it does make all of the clay particles repel each other. But remember, in a glaze formula, clay is only about 10% of the formula itself. But in a glaze, it actually, this is where it gets confusing. In a clay body, we want all these clay particles sticking together nicely, right? But in a glaze, we're using them to a different end. Okay, in a glaze, we've got all these particles that are basically randomly floating through water, and they come and they bounce off of each other, right? And that makes it essentially random because, if you've got your 2 clay particles here, well, maybe they'll magically hit with the 2 flat sides to each other, but more likely they're going to come at each other like this, or maybe 2 positive sides, and they'll bounce off each other, or anything like that. But when you add the dispersant, it actually sort of locks everything in place because now they're all forcing each other to stand in line. You know, it's like a bunch of soldiers who no longer have personal space. You must be exactly this far from you and from your neighbor. So they don't bounce. They repel and they stay suspended. The glaze doesn't just settle to the bottom, but now they're sort of forced into order and staying into a formation. And so that helps them pack more efficiently.
Right. But if you add too much Darvan, your glaze will settle in the bucket, right?
Yes. You can definitely over disperse a glaze, and that really comes down to dispersants are a really cool thing. Okay, dispersants work by coating exactly one face of a clay particle, just the positive face. Okay, and so if you have excess, it begins to coat the edges, and then it really changes the chemistry, and so it starts to fall out. On top of that, it will actually begin to affect the silica as well, and then everything starts to fall out of suspension. So you can definitely over disperse a glaze or a clay. It's not terribly tragic, but things become very rubbery. And so that's why actually you can calculate exactly how much dispersant you need for a clay body. We could do dispersant calculations for you. It wouldn't hurt, but most likely your glaze batches are going to be so small, you wouldn't get accurate amounts of Darvan anyway, so you probably just want to go as close as possible. Now, for you, the other thing is sort of talking about the water. That you do want to keep. Well, I guess this is the part I haven't quite decided yet. Probably you want to keep the water content consistent. So, like 80 mils of water for every 100 grams of glaze. That's or maybe 90, depending on what your sort of base glaze comes out as. When you add the dispersant, it might make it super liquid. It probably will make it super liquid. But I think probably just go with it, and we'll cross that bridge when we get there. Okay?
I have a lot of test tiles to make still.
Yes, and you've got a beastly little kiln.
Yeah, it's awesome.
Sue got a new test kiln.
Yeah.
Cone 10's a beautiful thing, but you're going to burn it out, so, don't push it too fast.
Yeah, right. My other question was, can I fire cone 6 clay to cone 10 and get accurate glaze results? Like just on a test tile?
What do you mean by accurate glaze results?
Well, is the fact that it's cone 6 clay going to affect how the glaze looks or behaves when it gets to cone 10?
Do me a favor. Since we're being recorded, can you type the name of your clay manufacturer in the text box, since the text box doesn't get recorded?
Sure.
Sorry, I know a lot of people. Okay, yeah, that's what I figured. I know a lot of people in the industry, and I don't want to piss them off because I'm about to talk smack. I've been dealing with that company personally, and it's probably fine. Give it a test. But I know that their cone 6 clay doesn't actually absorb until cone 8. Or doesn't vitrify until cone 8.
Great.
I think I showed you those numbers at one point. Maybe not. This is the whole cone 6 fallacy. That the clay companies think that 3% absorption is okay at cone 6, and it's really not. I fired that clay or some of their clays to cone 7, and only gotten to 0.75% absorption. Under 0.5 is vitrified, for everybody who's wondering. So it'll probably be fine. But, test it first. Put a piece in the test kiln next time you go to cone 10.
Well, I made my cone packs with the Cone 6 clay, and the clay is very nice and glassy.
I bet
Like,
it's.
it looks nice.
I bet it's a nicely vitrified porcelain. Hold on, let me pull up your Facebook pictures. Yeah, I mean, did the cone packs stick?
Yeah.
They did?
So, stick to the kiln shelf?
Right.
No.
No? Oh, then
Nope.
you're probably fine. Let me see. Oh, yeah. It looks fine to me. I mean,
It feels nice.
there might be a little bloat here or there. I mean,
Right.
you know, you're inherently overfiring it.
Yeah.
But 2 cones, if it's actually not vitrifying until cone 7.5, it's probably okay. You know, just be careful that kiln overshooting. I mean, it's all manual controls, just dials.
One dial.
One dial.
Yeah.
Yeah. So just watch your heating rate. Did you
Right.
just turn it on and let it go for that firing?
Yeah.
Yeah. Okay.
I just wanted to know what cone it would go to. So.
Yeah, that's a good cone 11 at least.
Yeah.
Okay. Cool beans. Any other questions?
Okay. Nope. Not
Nope.
me.
Cool. Kevin, you mentioned that you should change the other materials rather than the flux when there are issues. I know that the flux is one of the main changeable factors in making a glass batch hotter, faster, and for longer. Is this because of wanting more temperature control? Well, so for the fluxes, the catch is actually going back to Phyllis's question. And again, so actually Kevin is a glass worker, so sort of teaching about like blowing glass and glazes. They're following the same trajectory, but the problem is we'll get into later in the class a lot of things like color specifically, and sort of what we were talking about with Phyllis, where in ceramics we do a lot of altering the chemistry to get different textures, but as well with getting different color reactions. That happens because of what fluxes we choose. Okay, and we will get into this in depth later down the road. But for you, where most color comes manufactured, you know, color rods or powder, it's actually pretty much stable in its own form, so it doesn't matter what fluxes you choose. As far as the temperature, it's not really a temperature issue per se, so much as a durability issue. Okay, having too much of certain fluxes makes the glaze very weak, and from a food safety standpoint, that's a problem. Okay. When we talk about temperature control, we try not to alter the fluxes to change temperature, because the changes that you make to get the temperature down is the same thing that makes the glazes physically weak and not food safe. There are other ways to alter temperature. Specifically, we use boron as an additive material, and I don't know what's in most blowing cullet. Soda lime silicate, you know. But with the borates, boron will bring down the melting temperature. So that's how we want to control temperature. And obviously, I know that boron is a common glass ingredient going all the way back to Pyrex and all that kind of stuff. But I don't know if it's common in lamp working glasses. I would bet it is, unless they're still using leaded cullet. Although lamp working can be high temperature, I would bet that it's a borate because you want regional temperature for lamp working. You know, because you've got the center where you're working is incredibly hot and melted, but you know you're still holding the outside. So that thermal gradient. The difference in temperature from the working area to the exterior is a lot of stress physically on the glass, and boron really helps with that sort of stress. Yeah, cool. Abby, did you have any questions?
Nothing specifically, no.
Okay. I know it's a lot to take in, but go with the flow and you'll follow along. I mean, actually, the fun thing that we'll do over the next couple of lectures is actually we sort of go backwards and cover a lot of the subtleties of the chemistry that we're sort of taking for granted here. But in the last Thursday's lecture of sort of talking about how glass works, how silica works, becomes really, really important to understanding what's going on in our glazes. And I know that today's lecture is probably a little bit abstract, just sort of going right into the calculations. But the short version of those is some of the background from Glazes 1, wherein the calculations are something that reflects the basic chemistry of the glaze. So every glaze can be analyzed for its chemistry, and we have this UMF system for looking at that chemistry. So it just helps us speak in a shorthand, which doesn't help for your comprehension at the moment, but you'll follow along. The best thing that you can do is, if you really want to dig into it more, try my current favorite website, glazy.org. And just go and look at some glaze formulas and poke around. And what's great about Glazy is that he gives you the formula. Most of the time there'll be a picture of the glaze so you can see what it does. And then he also traces the chemistry. So he plots the unity molecular formula of the glaze. And it's really a beautiful, beautiful website. I really, really love it.
Mm-hmm.
Cool. Phyllis, do you have any more questions?
Yes.
Cool.
Okay, so going back to Sue, what percent of Darvon did she use? Did you use, Sue? And how did you determine that? That's one. Number two, does it make a difference in pinholing if it's a gloss versus a matte? And three, what I've observed is that when people trim pots and don't kind of heal it back over by recompressing it, you really tend to see a lot of pinholing. Which might fit into your porosity concept of more open pores. I don't know. And then I recall you mentioning that commercial dinnerware is primarily made by firing to vitrification and then glazing. So do they have pinholing problems?
All great questions. Sue, do you want to answer the Darwin question first?
Sure. I didn't really, I just added drops until I noticed the glaze thinning out. I didn't have any real scientific way of doing it. Yeah. It was the first time I did.
What was your volume of glaze? A gallon? A liter?
500 grams.
Okay.
Yeah, and so I just kept adding drops and stirring until I noticed that it was much thinner than it was before, and then I stopped. Well, the first time I did it, I overdid it, and it all settled in the bucket. So then I got cautious and kind of scaled back a little bit.
Yeah, we should do your dispersing calculations when we do it this time, just to make sure we're consistent with what we're adding. And that's pretty easy. I've got a little calculator that'll do it right quick. So as to let's see, what were your two questions? One of the trimming. Yeah, great observation, Phyllis. In fact, that's something that might even be worth looking at, because you're exactly right. When you're trimming and not compressing, you're exposing clay of inherently different porosity. And different porosity becomes a huge problem. In clays, we see this in the result of S-cracks, okay, the cracks right through the bottom of your pot. And one of my other regulars, Peter, did some testing recently where he had pots that were giving S-cracks. And what he could see was that the density on the rim of the pot was radically different, orders of magnitude different than in the foot of the pot. And so that you get that kind of stress from different compression. And so the same thing absolutely applies. If you're forcing those particles together through ribbing or tooling, in certain areas and not in others, you absolutely would get different density of pores and then different application methods, and the rise of pinholes absolutely could happen. That's a great observation. And it's probably something to consider with Sue as to look at. For the commercial dinnerware, do they get pinholes? Yeah, they do. Not as much. But for a very specific reason, and actually it comes down to application method. Commercial dinnerware tends to be applied with a spray. Okay, so for everyone who doesn't know what we're talking about is that in dinnerware, fine china, right? Is this Limoges? Oops, with all my paper clips in it. My little Limoges dish here. What they often do is that they bisque to cone 10. And this does several things. One, if the pot's going to fail, if it's going to crack, if it's going to warp, it's going to happen in the first firing. So they don't waste the time and energy on putting it through glazing. That's man hours, that's material, and then the second kiln, that's more kiln energy. That's really the big reason why they do it. There's some other technical reasons, but the big one is that it's saving on energy. Then the pot ends up completely vitrified, so there are no pores, so theoretically the glaze won't stick to it. The way that they overcome this is that they literally they put the pots in the glaze line, they put them on a conveyor belt, and they hit them with a blowtorch, literally a big open flame, like right onto the pot, and then immediately they're hit with a spray. Okay, and spraying creates what are called atomized particles, and what they are, they're tiny little balls, little spheres of glaze. Okay, because you spray the liquid glaze gets displaced with pressurized air, and it breaks it up into tiny little nodules, and then those hit the pot, and the heat from the blowtorch evaporates the water, and you get all these tiny little nodules. Well, packing spheres is a really inefficient way to pack, right? If you've got a room full of balls, it's really poorly packed versus a room full of cubes. If it's cubes, there's no negative space, but if it's balls, you get, a fair amount of negative space. In fact, I just saw the calculation the other day, and I forget what it was. Anyway, it's like 30%. And so with that application, you can still get negative space that can still be pinholes. It's less so than in the sort of conditions that we're talking about, but it's definitely something that can happen. Was there another part to that, Phyllis?
No, I mean, I knew it was to find the defects, but I was just curious if, based on your theory that it would be totally vitrified, thus there would be no pores if
right.
That was a problem. I was approaching it more from that side.
Yeah, it can be just because it's still a particle packing problem. Yes, Kevin, 30% negative space.
And is there a difference in a glossy versus a matte? Like, as the glaze gets glossier, do you see less issues with pinholing?
That was the question, right? Sue, I forget the chemistry on Woo. Was Woo a fake matte?
It was, but it's not anymore.
Right, you reformulated it.
Yeah. And I definitely, like with that recipe, the glossier I let it get, the less pinholing I saw. And like I've done lots of different glaze tests, and I'm finding that the matte glazes pinhole more than the glossy glazes. But I have a specific glaze that pinholes all the time, and it's a glossy glaze. So, yeah, there's no theory there.
Right.
Yeah.
Well, because it comes down to what is the physical structure of the particles in the glaze. I mean, the fact that you have a glaze that pinholes all the time means that there's something about the physical particles and the way that they pack together that generate the negative space and generate the pinholing. Actually, that's quite beautiful. And now someone else might say, oh, well, it's, the big argument that came up in the greater discussion of what Sue's talking about was there was a person who was claiming that it was the degradation of strontium. So in the glaze, you have strontium carbonate, okay, which is literally a strontium oxide molecule bonded with a carbon dioxide molecule. This person was arguing that the carbon dioxide comes off from the strontium and creates a bubble in the glaze. Okay. The problem is that this is nonsense because it's very easy to run a test where you fire off strontium carbonate and you can track the fact that they disassociate at roughly 900, 930 C. This is a glaze that's being fired to 1260 C. And we'll talk more about how glazes melt later in the semester, or in the term, but that really it's not till the last 100 degrees of a firing where glazes are actually melting. Other than that, it's just a bunch of raw materials sticking together. So under this person's theory, the notion that if it is gas escaping and making these bubbles, it would have to happen between 1160 and 1260, which is cone 6 where this glaze was really fired. Well, we know that strontium disassociates at about 930, which again is 230 degrees before that ever happens. So again, that theory is nonsense. Now, as to the gloss versus the matte, yeah, it should be relatively independent. The fact that the mattes do it more, I would bet has to do with the crystallization of the glaze and creating a surface tension on it so that it doesn't heal over as much. Because a lot of glazes have these pinholes, and if you look at glazes that are dimpling, a lot of dimpling in a glaze where you look at, again, going back to the beginning of the discussion of an even surface, when you see dimpling, so it's a flat surface, but there's all of these little dimples, are essentially healed bubbles. Okay? And so to have a glossy glaze, theoretically the glaze has the viscosity to overcome a lot of that. But with a matte glaze, as the crystals precipitate, it creates a surface tension that probably doesn't heal as well. So yeah, I could definitely see a matte being more likely to have pinholes. Going back to this original glaze, though, it wasn't even a true matte. It was a fake matte, meaning it was literally just under fired. And so again, the notion at all that this was degradation is once again bunk, because the glaze is never really melting anyway. So if it's not really melting, you're not really trapping bubbles inside of the glass formation. It's just bunk on top of bunk. And I'm trying to hold my tongue as best as I can.
One thing I noticed with my glaze my glossy glaze is when I overfire it, because it changes from matte to gloss really fast. So it's like a half cone between matte and gloss, and so it's when I'm overfiring it that it pinholes. Almost every time. So yeah, that was.
What do you mean it changes from matte to gloss really fast?
So my kiln is very uneven. So when I put pots in the hot part of the kiln, they turn glossy, and the pots that are in the cool part of the kiln stay matte.
And you looked at the chemistry of this glaze?
Oh yeah, this was before I learned anything.
But if it's matte, then it's underfired. It's just underfired. If a matte glaze turns glossy, it's just an underfired gloss. It's not actually a matte glaze. Yeah.
So basically, like if there's like one cone between when it's matte and when it's running off the pot. So it's
well, okay. So let me change some of your language, and I don't want to speak for you, but again, we have to be really careful, because what you're actually saying is there's a one cone difference from going underfired to fully melted. Not overfired, just melted.
Okay.
Now that melted glaze may have a very low viscosity. But it's not that the glaze is running, per se. It's just that you've got a glaze that, once it melts, has a very, very low viscosity. It's going to flow very, very evenly.
Right.
Okay? But this is an important distinction. So really, what the problem is probably... let's go back. The fact that you see the pinholing when it's glossy, when you fired it to the right temperature. Well, this goes back to that notion of the fact that it's melting means that the bubbles are emerging. Okay, because remember, what's happening is that once the glaze is viscous, okay, once the glaze is melting, that the bubbles can swell, and that is part of the problem that happens with the pinholes. That as the glaze is viscous, the bubbles swell, and they can coalesce. Two bubbles can grow together, or many bubbles can grow together, and they will pop, causing the pinholing to happen. So if the glaze is under fire, it's inherently not viscous, so it can't do those things.
Right.
As soon as the glaze goes viscous, now it can coalesce, expand, and pop. Okay, so again, the sort of the important distinctions about what's going on in the glaze itself. If the viscosity is low, I'd probably up the silicon alumina, stiffen it up a little bit. We could look at the glaze chemistry another time and talk about it.
Yeah, well, I haven't been using it since I took your class, so.
It sounds like a funky glaze.
It's a funky glaze, yeah.
Cone 6?
Cone 6, yeah, 0.5 flux ratio, and it has like 4% lithium carb, and yeah, bunch of stuff.
Oh, it gives me heartburn. Lithium carb. The lithium carb thing, when we get to the 04, it just pisses me off so much. Like, so much of 04 is lithium carb everywhere. And it just we'll get there. I know. It's the things that people do to make Cone 6 happen. Makes me sad. Single tear. Any other questions?
I just downloaded your UMF calculator public 2016 testing matrix, and it's coming in as read only.
It shouldn't be. I think it's a security setting on your computer.
Okay. That well could be.
Yeah, and so I think if you just click around, you should be able to get rid of it. I didn't put any locks on that one.
Okay. And it actually looks the same as the old one?
It is. So what the testing matrix version does is that you'll notice that there's either 10 or 11 sheets on it. I forget what it is. I think it's 10. And what it is you put a different formula in each sheet, and then at the end there's a sheet that says collective.
Yes.
And that just takes all of those formulas that you put on the 10 individual sheets and puts them on one sheet that you can print out and bring to the studio.
Yes. So does the old one.
Does it?
Well, mine does. I finally opened the collective tab and said, oh, look at that. But what I'm curious about is the lovely colored boxes. They look like the old ones, and I thought Iron was going to do something different because you had rearranged things.
That is, let me see if on Blackboard, if I posted, I don't remember if I posted the testing matrix with FE, because that's the one that incorporates Iron.
Yeah, because this one looks like the old one that we used last session.
There is a testing matrix with FE, obviously meaning Iron. Hold on, just coming into Blackboard. Special effect. Documents. There is with FE UK. I had a British student last Christmas, so I made one for her. I'll add it right now. Hold on one second.
Okay.
We will get into the Iron. As I mentioned, I think in the introductory lecture, there is an entire lecture in this series that is just on Iron. So it's a big subject. And the short version is that we're still working on the research to put it all together to make it solid.
Mm-hmm.
Okay, it's up now. It's the last document.
Okay.
But I think we'll talk about it in the lecture. It works pretty well. The iron and the manganese. The question that I keep getting asked that I don't have an answer to is when do you really need to begin considering iron? And that I don't have the answer to yet. That's what I'm still sort of trying to figure out. I mean, the easy answer is, well, always. The short answer is, or the real answer is, I don't really know. I still have to work on that.
And are you going to talk about iron in the clay body, your darker clay bodies, or just in the glaze, or both?
Mostly in the glaze, but it does come up in clay bodies too.
Will that be part of the lecture? Maybe.
I don't remember. Let me see. Talk about iron oxide. No. Yeah, it does come up a little bit in clay bodies. Specifically as a low temperature flux.
Okay.
Yep. Anything else?
Not today.
Not today. Okay.
The garden is calling.
The garden is calling. Okay.
The garden is calling. The outside is calling.
That's because it's still 6 o'clock there. The sun is set here already. Okay.
Right here till 9:30. It's gorgeous.
Oh, well, let me see. It's 9:02 here. Oh, and I can see a lovely cotton candy sunset outside my window. Okay, so the next two lectures, the next 4 lectures or so, we're going to dive back into Stull pretty heavily. It's a series, I call them the subtleties of Stull, so it's a lot of calculations and subtleties of chemistry, but we'll start to talk about the effect of the different fluxes. We're going to start to talk about really looking into phase diagrams, which is something in Glazes 1 I sort of say, we're not going to talk about that. Well, unfortunately, now it becomes a serious reality. Talking about different effects of texture, as we started to talk about before here, talking about how it affects iron, how it affects manganese. We'll talk about thermal expansion. Actually, that won't be this week. Thermal expansion will be next week. So, these 2 lectures will really get into how flux selection works and how a bunch of the things that we can learn from the Stull map that we haven't talked about before. So it's a lot of fun. This class we really hit the ground going with a lot of cool stuff right off the top. I will apologize to, especially to Phyllis and to Sue, and to Bumkey, who's watching and not with us, of in the next lecture, I admit that I've been lying to you.
We knew that.
No, just the way I told you that cones work is not actually literally exactly how cones work. Especially the lower cones, but we'll get there. You'll see in the next lecture. There's some tweaking to chemistry. Like the idea is the same, but just to get through the lectures, I sort of simplified what the actual chemistry was. You'll see. I apologize, mea culpa, but now you're all here. You've all drank the Kool-Aid, so. Okay, so any other questions? We good? Alrighty, folks. I will see you all next week. Enjoy your week. Don't spend too much time in the sun. You've got videos to watch.
Oh, the next one comes out what day? Thursday?
Thursday, yeah. So it's going to be a Monday, Thursday release schedule.
Okay, thank you.
Alrighty. Talk to you later.
Bye.